Hello and welcome to Embedded Internals. This is second episode of our series, Memory Thinking series. In the first episode, we have seen that memory are actually virtualized. In this episode, we are going to see what does that virtual world actually look like. Let me show you the code first. This is our code to print few variables like first is global var, which is a global variable having a particular value. So it is a initialized global variable. Second is stack variable inside the main function. Third is heap variable, which is used for dynamic memory allocation. And we have printed the address of all these variables. Okay, so this is a very simple program. All the programs which we are using in this episode is available on our GitHub channel. You can check from there. Let us compile this code. See the pattern of addresses which we are getting. In the stack segment, we are getting address from the higher address range, that is 0FF D64 something. Whereas the code and the global variable address range is almost adjacent to each other, like 6265283114 and this. Okay, this it seems they are adjacent or to each other. So check the heap variable. It is also near to the code or global variable and farther from the stack variable. Let us run this program again. Similar behavior is being observed. Why these addresses are so different? Why does the stack leaves near this particular higher address range starting from 0FF, zeros into 7FFE, all these? Why the code and global variables are near each other? Who decided this memory layout? Today, in this episode, we will walk through this hidden architecture of every Linux process. This is the process PID is 3366. Okay. I want to show the process address space of this PID. We know that proc file systems gives the live status of the running process. So our running process ID is 3366 and we want to see the memory. So this is the memory. See, all these memory range belongs to our process, which is a demo one. Okay. And we have seen that heap segment lies in 59178 AE to this particular zone. This is the memory range. This is the permission associated with this, that is read, write, and P stands for private. This is the offset value. This is major and minor number, and this is the inode value. And this is the memory region. This memory range is map to. Okay. Now let us see, is the heap memory coming from this range? See, heap is from similar range 59178A. 8A. Okay. Similarly, we can see for the stack variable as well, 7FF D288. You will get from this memory range only. Similarly for code and global. Let me show you again if this range remains similar in the process address space or it's differ. Now the range is 5A. This process ends. Okay. Let us find what is the new process ID. New process ID is 3373. So cat /proc 3373 maps. Now check the range. 58 A8 to E1, this range, and almost we are getting from this range only, 82 range. heap variable, stack variable from the higher memory range, D6F0 to D6F0. Okay. And every time this process address space memory ranges are also changing. Now question is, what is the actual process layout? Question is, what is virtual address space? The memory which is visible to a process. Okay. This is not the actual RAM or physical RAM, or this memory does not have any link to the hardware layout or the raw memory. This memory is actually an isolated virtual memory map provided by kernel. Let me show you an example. This is a process 1. It has the memory, complete memory range, having the own stack segment. This is stack segment. Similarly, libraries, SOs, data segment, BSS segment, text segment, all these things. And this memory starts from higher address to lower address. Same process, at virtual address space or layout belongs to other process as well. Complete memory range. So every process thinks that the complete memory belongs to its only, with all these things. Similarly for process 3, process 4 and process nth process, whatever multiple process coexist simultaneously at the operating system. Every process gets its virtual address space layout. So suppose there is a memory address which is 40000000. So this memory range will fall in this address space range as well, in this address space range as well, and this. So every process P1 believes that it uniquely holds this address. Similarly, P2 also believes that this process uniquely hold this address. And fortunately, both the processes are simultaneously true, because complete virtual memory range belongs to them. But what actually true is, this is the virtual space. Same addresses may exist in both space, both processes, but the mapping, kernel memory mapping will be different. So address may remains the same for two process, but internal memory mapping of that address to the physical layout will be different, which is done by the Linux kernel. So this way, virtual addresses are local to process, but when we say the actual mapping, they are global. So that differs for each processes. So the question exists, why virtual address space exists? If we don't have the virtual memory, every program would need to know where the RAM is, because now the program only knows their virtual address space layout. So this provides the process isolation. Okay, because Linux or kernel provide every process its own address space, and the address space is of consistent layout. First thing it is preventing, it is doing is protected isolation. Protected isolations mean now one process will not accidentally overwrite the memory region of other process. Problem of data corruption and the data crash will be prevented, and the kernel security will also be maintained by this process, as now we have protected isolation. This provide the protected isolation, and which further provide the security inside the kernel. Now the processes will not accidentally overwrite each other memory. Simplicity, as they are not bothered about the real RAM, multitasking will be possible, is possible because of this virtual memory. Every process have their own address space range. They continuously working with their own address without worrying about the actual RAM. And scalability. So this is the benefit of having the virtual memory or virtual address space uniquely to every process. Without virtual memory, memory management will be chaos. Let us cover the third point, virtual address space layout. This is a very important topic of this episode, today's episode. We have covered what is virtual address space and why virtual address space is needed. Now, full virtual space layout. Address range, this is high address and here it is low address. First is initially our kernel space rises. So it is kernel space. And in the process address space range, we have stack. Stack segment. Stack segment grows downward. Then we have memory mapped regions, mmap, and the shared libraries, .sos. Okay, and after that we have heap segment. Heap segment is for dynamic allocation and it grows upward. We have BSS segment for uninitialized global variable, uninitialized global variable. We have data segment for initialized global variable, initialized. And at the end we have text segment where our code part exists. So this is a very important diagram. I will say everyone to memorize it by heart. Every reason has a purpose. Associated permissions we have seen in our memory maps. Growth direction, like stack is growing downward whereas heap is going upward. Behavior, what exists is in which segment, as well as ownership. Let us start from the lower addresses. So text segment, executable machine instructions. So the complete code, ELF or what is inside the ELF, what is written in the code exists at the code section only. So we can say it is like compile binary code, executable. This text segment is usually read only. So the permission associated with it with text segment is read permission, read only, and executable also. It does not have any write permission. So when you write the main statement, this is actually this part goes into the text segment. Write permission we have not given so that it prevents self-modifying code and improves security, because with when we give the write permission, security will be the issue. Now the second segment is data segment. We have different type of variable, local variable and the global variable. Global variable or the static variable having the global scope which are initialized goes into data segment. This is a global variable, global var. This will go into the data segment part. This is a initialized global variable, so it is going into the data segment part. If similarly we will write uninitialized global variable like int, this will go into BSS segment. We will show. So initialized global variable goes into data segment, whereas uninitialized goes into BSS segment. Let me int global variable in the global section will go into data segment. Why? Because it is pre-initialized. And the permission associated with data segment is read and write permission. Because global variables can change. So we have given the read and write permission. Similarly, similar way we have a BSS segment which is block start by symbol. We have declared int global where uninitialized un that will go into the block segment. One most important insight here is value does not stored in the ELF executable but is loaded by the kernel during loading during runtime also we can say. Memory allocated by using dynamic memory allocation goes into heap segment. They goes into the heap segment. So heap segment exists for runtime size memory, because in the dynamic memory allocation we know the size during the runtime. So runtime sized memory, and they have flexible lifetime. It's on our programming logic when to free the memory. Example from our code, we have demonstrate malloc. We have allocated memory by using malloc library function call. This will go into the heap segment part. Memory is managed by allocator and backed up by kernel mapping. Every local variables, function frames, return addresses, and the saved registers is in the stack segment. Growth direction is toward downward. So whenever you have any function call, a new stack frame will be created. Memory mapped region, or we can say mmaps. This is used for shared libraries, .sos, large file mappings, large allocation, file mapping, sometimes enormous mapping as well. See, we have these library regions. We also have libc.so, the high these region. There the library exists. These all are the shared memory regions, libc.so. We have enormous mapping that will go into the memory mapped segment. We have stack, we have libraries, ld linux still in the memory mapped range, and this libc.so.6 that will also go into memory map range. Okay, so see which all where the libraries is getting the address. Libc. This is our library, shared library, ld linux, this is a loader, this is, so everything has a mapping. This library, shared libraries have a mapping in the memory mapped region. Executable loading is mostly memory mapping and user space. Process lives in user space, whereas Linux kernel or the all critical resources lives in the kernel space. Okay, so like the memory, schedulers, file system, everything resides in the kernel space. Our process cannot directly access the kernel space. It needs a system call to access the kernel space. So user space, which is a safe zone where our code exists, but it does not have lots of unprivileged zone. There is a strict boundary, and then there exists a kernel space, which is highly protected zone and privileged and protected zone, where all the critical resources exist. Linux kernel exists. Whatever memory we need or whatever mapping is done by using the system calls, we request the memory from the user has their virtual address space, but the mapping is provided by the kernel, and user request the for that mapping to the kernel space using the system call layer. Why this separation is needed? To provide the security, stability, and isolations as well. So user required the mapping, Linux kernel mapping, to get the actual physical space. User has the virtual memory. To get the physical memory or the memory layout, they request to the kernel space using the system calls. So what happens when you load, you have a ELF, like in our case we have ELF demo1. Okay, this is ELF file. This is loaded by the loader. They provide the kernel provide the virtual memory mapping or process address space. When ELF is loaded, kernel first reads the, we say load the ELF by the loader. So we have loader will first read the ELF header. We will maps all the segments. So maps segments. segments like stack segment, data segment, code. They set the permissions, create stacks, and initializes the process. This has all this necessary information as well as the number of sections or size of sections, program section, and section header, program header, etc. This in the execution awareness series, we have a dedicated episode on ELF where we have explained ELF file in detail. If you really want to understand ELF in more depth, please go back and check that episode. I will link that episode in the description as well. All the necessary information whatever is required will be available inside the ELF file as well. Whatever the function call we are doing, just malloc, getchar, printf, all these function we have used, so these will be available from where the main function is been called. Everything is in detail. We also have one dedicated episode on what happens before the main in our execution awareness series, ASLR, address space layout randomization. This is a best modern system concept. We have seen that when we run same program multiple time, every time we are getting the address from the different range. Every time address we are getting are random values, not similar addresses we are getting. I will show you from the code as well, then we will go details. Run the code again and again, /demo. The address range is different. Again, address range is different, 64, 60, every address range different. 5C, 62. So when you run code hundreds of time, you will get the address from different ranges. So Linux is randomizes stack segment, heap segment, mapping, and libraries. Because when we see, so we can say that Linux is randomizes stack, heap, mapping, and library addresses. And what's the benefit of this? Benefit is that it prevent the hack. It's a first is security. Our code as the new memory range addresses are given every time, hacker will not able to hack the system easily. So prevent hacking. So secure it tightens the security and exploit mitigation. So we have seen that memory layout is structured but intentionally randomized. Structured. If you don't want the this random memory addresses, can we do that? Yes, we can do that. I will show you in the kernel. There is a file randomize VA space, virtual space, where we have value 2, which is this is set by the kernel. Okay, I don't want the random variable every time, so temporarily I am just removing this randomize very virtual space functionality. So we can simply say ctl. This is a kernel variable, so we will go into kernel as 0. Okay, now check the value 0. Now run the program again and again, same program, /demo. What address range you are getting? From 5555, and this is this. Again run. See, same address. Address is not being, you are not getting the random addresses now, same address. Then hundreds of times you will get the same address. Even when you check the memory of these, virtual memory address space will not change now. Same 7F. Functionality to randomize the virtual address space. Now we have temporarily disabled it. Let me remove that. To value again. Value is 2. Now run the code. Different address. Without ASLR, address will stabilized. One thing I want to clear it out, that virtual memory space is not equal to physical memory usage. This is local to our process. In the coming episode, next episode, that is episode 3, we will go inside the stack segment. So that will be the stack segment internals. Thank you. Stay tuned.